Okay, so now in this video, we want to look at some further logically equivalent statements, which will be really important for us later in various different proof methods that we're going to discuss after this chapter on logic. So let's look at the following truth table. So we're going to have P and Q, of course, as always, and we're going to need all possible values there for P and Q. And then we're going to look at the implication. We're going to look at the negation of the implication. And then I want to look at two other columns just to, as an exercise, but also to notice an important equivalence. So we'll do not P and Q, and we'll do P and not Q. Okay, so of course, P implies Q we know is true, false, true, true, and then the negation of that would be false, true, false, false. Okay, not P and Q, so that's false and true, so that's false. You need them both to be true. This is false and false. This would be true and true, and this would be true and false. Okay, this last one would be P, true and false, so that's false. True and true, false and false, and false and true. So, okay, we just filled out the truth table, but now we notice that there are two columns which are the same, so they must be logically equivalent. There's the not of the implication, and there's P and not Q. That means if you want to not the implication, you will get P and not Q. So you don't get some other statement involving implication, or at least not the way we're going to write it. You get this, right? So what we can state then is we could say this as a theorem, which is a theorem of logic, if you will, which is that to say that not P and Q is logically equivalent to P and not Q. Okay, good. So that's an important logical equivalence. And this is going to be really important when we do what's called proof by contradiction. So that's going to be coming up in the course. Let's just do an example of how this plays out in some things. So let's start with a statement in words. So for every natural number n, if 3 divides n, then 6 divides n. Okay, so we can rewrite S in quantified form. So for all n in the natural numbers, 3 divides n implies that 6 divides n. By the way, this is false, right? Because if 3 divides 9, but 6 doesn't divide 9, right? Okay, but we're just playing with the logic here. So now I want to know, okay, well, what's not S? Well, I just put the not out front. 3 divides n implies 6 divides n. Okay, so this will be logically equivalent to the not hits the for all and becomes there exists. And then I'm just going to stick the not inside for a second. Meaning that I've thrown the not through the expression, but I stopped right there, right? So I still need to, if I want, I still want to push the not through the implication. Okay, so that's logically equivalent to this first part doesn't change. And then we use the logical equivalence we just derived, right? So that's equivalent to 3 divides n, so you don't negate that. And it's not the case that 6 divides n. Okay, but we can use the mathematical notation now for not the case that it divides. So we can rewrite this one more time, that there exists an n in the natural numbers, so that 3 divides m and 6 does not divide n. And of course, that is the case because I already gave you the example, which is 9, right? Let's just give ourselves some room, but also let's just translate this back to a sentence using just English. So now it would say that there exists a natural number n which is divisible by 3 and not divisible by 6. And of course, that is true because, again, 9 is the number that exists so that it's divisible by 3 but not divisible by 6. Good. So this logically equivalent statement that not of an implication is the same as P and not Q is going to be very important when we do proofs by contradiction later. So that's one of the reasons why we need that logical equivalence. And then the last one that I want to look at is, and first we need a definition. So we want to look at the contrapositive. So the contrapositive of P implies Q is not Q implies not P. So that's just telling you what this word means, but now you'll see why it's significant here in a second, because we're going to do a truth table involving the contrapositive, which will show that it's equivalent to something else important. So let's start our truth table with P and Q again. And then true, false, true, false. All right, let's just start out simple here. So we'll do not Q and not P. And we'll do P implies Q. And then we'll do not Q implies not P. All right, well, the first two are pretty simple. So that's false, true, false, true, and false, false, true, true. P implies Q. This is the typical one that we've done a few times now. True, false, true, true. Now this last one, not Q implies not P. So we're going to use the third and fourth columns to do this. So false implies false is true. True implies false is false. False implies true is true. And true implies true is true. Okay, so that means that the implication and its contrapositive are logically equivalent. And this is an important fact of logic. And so I'll write it as a theorem. I'll even write it in words. Well, no, I'll just write it as the following. So P implies Q is equivalent to not Q implies not P, logically equivalent. Good. So we're going to use that in a proof method, which is called proof by contrapositive. So that's why it's important, because if you want to prove an implication, what this says is that you can also instead prove the contrapositive. And, you know, for now, you might not understand why you'd want to do that, but it turns out that sometimes it'll be easier to do that. Okay. But now let's just do examples of how to compute the, just to like work with this contrapositive, right? So for example, if n is even, then n is an integer. So in this statement, P is given by this, and Q is given by that. And so this is literally just equivalent to P implies Q. I don't think I want to write that in red. So this is P implies Q. And so then the question is, what is not Q implies not P as a statement? And so that is the statement that if n is not an integer, then n is not even. Well, notice if n's not an integer, then how could it even be even? Even is a smaller subset of the integers, and if you're not even an integer, then you can't be even, right? So it's equivalent to saying if n is even, then it's not, then n is an integer, right? So those are both equivalent. Let's just look at one more example of this. So if n is odd, then n is irrational. So here, of course, we can identify what P and Q are. This is P, this is Q. So this other one was true in both cases, they're equivalent. In this case, it's false, right? So P implies Q is false. And so because, well, maybe I should be a little more specific. So let's just say n equals 3 and n equals 3. So if n equals 3 is odd, then n equals 3 is irrational. This is false because n equals 3 is odd, but n equals 3 is not irrational. So the implication is lying to us. Okay, but let's just play with the expression. So what is the contrapositive? So the contrapositive should also be lying to us. So let's see. The contrapositive is if n equals 3 is not irrational, then n equals 3, then n equals 3 is not odd. Notice that's also false because n equals 3 isn't irrational, but n equals 3 is odd. And so this one also lies to us, right? Good. So this is the contrapositive. We're going to see way more examples of using the contrapositive when we talk about the proof technique of proof by contrapositive.